the new section, I'm going to talk about probability as a continuous set function. There's not too much to do here. We're going to have two definitions, one proposition, and then we're going to do three problems. Probability as a continuous set function. Let's give the first definition. Let event 1, event 2, etc. be a sequence of events. Such that E1 is contained or is a subset of E2, which is a proper subset of E3 forever and ever. Then the sequence of events is said to be increasing. Then the sequence of events is said to be increasing. Now, why is increasing a reasonable statement? Well, this here, say, is E1, and E1 is contained, or is a subset, of E2, which in turn is a proper subset of E3, and so on. It's increasing. E1 is here, E2 is bigger, E3 is even bigger. It is increasing. Now, that's the first definition. The second definition. If E1 contains E2, and E2 contains E3, and E3 contains E4, and so on, this sequence of events is said to be decreasing. The diagram will just be in reverse. E1 is going to be the biggest one. I guess it's going to have to be infinitely big. And E2 will lie in it. E1 contains E2. E2 contains E3, etc., etc. The reason they're going to have to be infinite, E1 and E2 are going to have to be infinitely large, is because there's an infinitely many set of events inside it. Okay, so now their most advanced definition. Now for the proposition. We're going to talk about or state a proposition about increasing and decreasing sequence of events. Proposition. If the set of events En, where n is an integer and it's at least 1, is either increasing or decreasing. It doesn't matter in this proposition. Is either increasing or decreasing. Then it will follow that the limit as n approaches infinity, as the number of events gets more and more and more, the limit of the probability of the E sub n's will equal to not the limit as n goes to infinity of En, but the probability of that. I mean, but basically you can put the limit inside there. Okay, think about why that's true. So we have this proposition and only this one proposition in this our section. Now we're going to do what I consider is a fun problem. We're going to do this problem 3 times. Each one will be a little modification, and the third one will actually use this theorem. Suppose you have an infinitely large urn. So you have this really, really large urn. It has the balls. It has many balls in it. The balls are numbered 1 and 2 and 3 forever and ever. Hence, infinitely large. Now, you want to put in 10 balls at a time and take 1 out. And let's even show that we're going to do this in a finite length of time. Forget about the time. Okay, first, put in balls numbered 1 through 10. Take out ball number 10. Second step, put in balls numbered 11 through 20. Take out ball number 20. Steps 3, put in balls 21 to 30, in, out, number 30. Okay, so you always put in 10 balls, and you take 1 out. And you do this forever and ever. And the question is, how many balls will there be at the end? How many balls will there be at the end of this? And you should try to think how you can do this experiment in a finite length of time. That's an exercise that I'm given. Figure out how you can do this exercise, this problem, in a finite length of time. But for now, let's assume we can do this in a finite length of time. The question is, how many balls at the end? And so now, there's going to be an infinite number of balls at the end. I mean, think about it. You're going to have an infinite number of balls. That's what you put in. You put in an infinite number of balls. Less balls numbered of the form 10m. 10 times 1, 10, 10 times 2, 20, 10 times 3, 30. Those balls are missing. Well, that's an infinite number. That's an infinite number. It's an infinite number of balls. For example, just 1, 11, 21, 31, ball number 41, ball number 51. That's an infinite number of balls. An argument will be, maybe we'll ignore the first one. Argument will be, well, yeah, okay, there's a 0 in front. The argument will be, ignore the first digit. Eventually in this pattern, you'll get to 220 and 230, 990, excuse me. They should have 1s at the end, I'm sorry. If you ignore just the first number, excuse me, you have ball 0, you have a 0 ball, You have ball 1, a second ball, a third ball, a fourth ball, a fifth ball, eventually 22nd ball, a 23rd ball, a 99th ball. And if you go on, 1, 7, 3, 2, 1, 4, 0, 0, 1. If you ignore that number, this ball number will be 1,732,140. And that's an infinite number. And that doesn't include the ones that end in 2, like ball 2, ball 12, ball 22, ball 32, etc. If you ignore the 2's, that's an infinite number. 0, 1, 2, 3, 4, 5, 6, 7. The whole numbers. Those are the whole numbers. That's an infinite set. And we're not including 0, 3, 13, 2, 3, 3, 3, etc. The only ones we're excluding is the ones that end in a 0. It's clearly an infinite set. It's clearly an infinite set of balls that remain. And we took out an infinite set. 10, 20, 30, 40, 50, 60, forever. That's an infinite set. Infinity minus infinity could be any number. You can come up with an example where infinity minus infinity can be any number. 0, 1, 2, -3, pi. All right, now we're going to change it. First step, put in balls numbered 1 through 10, take out ball number 1. Put in ball numbered 11 through 20, take out ball number 2. Then 21 to 30, take out ball number 3. Step 4 will be we put in 31 to 40, and out is 4. And we do this forever and ever. How many balls will remain? And the answer this time is none. There will be 0 balls. There will be 0 balls. And why is this true? Because in step 1, take out ball number 1. In step 2, we took out ball number 2. In step 3, we took out ball number 3. In step 4, we pulled out ball number 4. When will we take out ball number n? Answer. In the nth step, we will take out ball number 1, n. We will take out ball number n. You put in n minus 9, ball number n minus 9 through n, and you take out ball number n. How do I know n minus 9? Because this is 30, and that's 9 less. This is 40, that's 9 left. Whatever number I end in, I start in 9 before. Okay, so every ball will be taken out. Ball number 2,315,211 will be taken out in the 2,315,211th iteration step. Okay. Now, same problem. Put in 1 through 10, then put in 11 through 20, and put in 21 through 30, etc. And yes, each time we put in those 10 balls, we take one out. But this time, we're going to take out a random number. Okay, so first step is we put in 1 through 10, and we take out 1. Not ball number 1. Sorry. In 1 through 10, out out 1 ball. Step 2, we put in 11 through 20, and we take out 1 ball. Now, I didn't say the ball that we take out has to be 11 through 20. Whatever is in the urn, we just randomly pull out 1. We put in balls number 21 to 30, and whatever is in the urn, we take 1 out, whether that's ball number 23 or ball number 4. Whatever is in there, we take out 1. And again, we do this forever and ever. And the question is, like always, how many balls will remain? Now, this one is less obvious because before we knew the first part, we knew that balls number 1, 11, 21, 31 forever. Ball number 2, 22, 32, or ball 2, 12, 22, 32, 42 forever, all the way down to balls 9, 19, 29, 39 forever remained. And in the second step, in the second part, hence there was an infinite number of balls. In the second part, we pulled out ball 1, and then ball 2, and then balls 3. So there was a bit more obvious that the urn will be empty at the end. Now we're going to randomly take out a ball. We're going to randomly take out a ball. Okay, so let us make this definition. See if I remember how to do this following. Let En represent the ball number 1 is still in the urn after the nth withdrawal. Let En represent that ball number 1, or ball number K if you prefer, is still in the urn after the nth step. And the step is complete after we do both parts. Put in, take out. Step 2 is completed after we put in balls number 11 through 20, and we take out any old ball. Now, if I can show ball 1 is not there, and notice there's not going to be anything special about ball number 1. If ball number 1's not there, the same argument will follow that ball number 2 is not there. Okay. Now, what is the probability that the ball is still in the urn after the nth step? Well, initially, right before we take out a ball, there are 10 balls in the urn. And if you don't want to get ball number 1, pick any one of the remaining 9. Okay, now there's 9 balls in there, and step 2 says put in 10 more balls. So now there are 19 balls. And we want to pick everything but ball number 1. So pick one of the remaining 18. Now, there are 19 balls in the urn. And actually, we just took out 1. So now there's 18. And then we add 10 more. That gives us 28. Take any one of the 27 balls remaining. And when we do, there will only be 27 balls. Add 10 more. Take one of them. Don't pick one of them. So it's 36. Now, where does this end? Where does it end? Well, it ends after the nth trial, the nth step. Well, look at this. There's a counter up here. 9 times 1. Look, this is the first step. 18 is 9 times 2. 18 over 19 was the second step. This is 27 is 9 times 3, the third step. This is going to be 9 times n, the nth step. And if you notice, whatever the numerator is, the denominator is 1 more. In the second fraction, the numerator is 18, the bottom is 1 more. Third fraction, numerator is 27, the bottom is 1 more. In the last step, the numerator is 9n, the bottom, I'm going to make 1 more. That is the probability that the ball remains after the nth step. Okay, now, what is the probability that the ball remains at the end? The event that the ball remains at the end with a D is nothing more than the intersections of EI. EI, I goes from 1 to infinity. It has to be, if it remains at the end, then it has to be in E1, because E1 says it's there after the first step. And it also has to be there after the second step. And it also has to be there after the third step. And this goes on and on forever. And shorthand notation is that this is just the intersections of the EIs. So the intersections of the EIs is the probability that is there at the end. But now, this is our sequence. Is it increasing or decreasing? Okay, let me put it down here. We should note that E1 contains E2, which in turn contains E3. And this goes on forever and ever. And why is that? Because if you remained, say, after the third event, after the third step, then you must have remained after the second step. Okay, how can ball number 1 be in E3? That is, it's still in the urn after the third step, but not be in the urn after the second step. Okay, we're not touching E1 unless we pull it out. That is, if it's there after the 50th step, it had to be there at the end of the 49th step, and at the end of the 48th step, and so on. It had to be there earlier. It isn't like we can take it out in the 7th step, and then by magic it'd be there in the 49th step. Okay, so these are decreasing. And you don't have to worry, is it increasing, is it decreasing? Because the theorem or the proposition says it has to be for any one of them. Okay. So now, the probability that the ball remains at the end is equal to, so I just wrote P of this. So it must equal P of that. It must equal P of the intersections as I goes from 1 to infinity of EI. Now, that's the same as the probability of the intersections of EI as I goes from 1 to n, but then we take the limit as n goes to infinity. No, that's not true. This here, or what's inside the brackets, is the same as the limit as n goes to infinity of the intersections of EI as I goes from 1 to infinity. But now our proposition says we can take the limit out. We can take the probability of the intersections, we can take the probability of the intersections of the EIs and take the limit of that. We can pull the limit out in front. This is the limit as n goes to infinity of the probabilities of the intersections of the EIs. Okay. But now, what is the intersection of the EIs as I goes from 1 to n? Okay. E1 intersect E2 intersect, etc., intersect En. Well, this is En, because you have E1 being the biggest and E2 being inside. Well, the intersection of those two is E2. What's common in here and in here? E2. And E3 is inside there. What's common to all three of those? E3. Okay, so this last line, this last equation, is nothing more than the limit as n approaches infinity of the probability of En. Right. So, obviously we need some more space. So let me write down the important part. That is the last things we wrote. The very last thing we wrote is that it equals the limit as n goes to infinity of the probability of En. And what I had at the very beginning of that equal sign is the probability that ball number 1 remains at the end. Okay, what is the probability that the ball remains at the end? And we defined E sub n, and now we know it equals to the probability of En as n goes to infinity. Okay, but we also knew that the probability of E sub n was 9 over 10 times 18 over 19 times 27 over 28 all the way down to 9n over 9n plus 1. Which in shorthand notation is the product of 9n over 9n plus 1 as n goes from 1 to infinity. If n is 1, this is 9 over 10. Got it. If n is 2, 9 times 2 is 18. 1 more is 19. That's this one. I do have one slight error. I shouldn't be going to infinity. So I need to get rid of this. Sorry. But you always check your work. You make sure that it starts off right and it finishes right. It's going to be the product as k goes from 1 to n of 9k over 9k plus 1. So instead of k, I put n. But it's still going to give me 9 over 10 when k is 1, 18 over 19 when k is 2. Eventually, k is n. So you'll have 9 times n, which is exactly my numerator here. In the bottom, you have 9n plus 1. Exactly my bottom. Okay. So, this is really the limit as n goes to infinity of this. But this is the product of 9n over 9n plus 1. Now, I want to show that the probability that the ball remains is 0. I want to show that that's 0. That ball number 1, the probability that it remains is 0. And like I said earlier, there is absolutely nothing special about ball number 1. If ball number 1 doesn't remain, well, wherever you see 1 in this proof, put 2 or 3 or ball number 98. It won't be there. So now I just need to show. So now probability is kind of done. I need to show that that product is 0. I need to show that that product is 0. And once I do that, I'll be okay. All right. Now, looking at this, I really don't know how to show that that's 0. Okay, it's enough to show, okay, that the reciprocal of this product now, let me not say it that way. I'm just going to talk about equivalences. If you multiply those numbers at the top right forever and ever, and you get 0, then multiplying their reciprocals should give infinity. The limit as n goes to infinity of the product of 9n over 9n plus 1 is equivalent to the limit as n goes to infinity of the product of their reciprocals. 9n plus 1 over 9n is infinity. Oops, this equals 0. The limit of this equals 0 is the same as the next limit of that being infinity. All I did was take the reciprocals. Okay, for example, if 1/2 times the third times 2/3 times the 7th is 1 over 42, well then if I take the reciprocals, 2 over 1 times 3 over 1 times 3 over 2 times 7 over 1, excuse me, I'm going to get the reciprocal. I'm going to get 42 over 1 or 42. I just get the reciprocal. Okay, no magic there. Okay. So, I think it'll be easier to show this equality. show that the left side, that limit, equals infinity. Okay, but even that's going to be a bit tricky. Now, that's the symbol for all. For all k bigger than or actually equal to 1, we're going to have this, that the product as n goes from 1 to infinity of 1 plus 1 over 9n. That's exactly what I have here. 9n over 9n is 1 plus 1 over 9n. So this here is exactly what I have at the top right. Now, this is going to be bigger than the product as n goes from 1 to, say, m of 1 plus 1 over 9n. Now, why is that? Why is this left going to be bigger? Well, this is pretty much the same as what we have on the left, except we stop at m. Now, each of these numbers that we're multiplying, here or there, are bigger than 1. Remember, this product, 1 plus 1 over 9 times 1 times 1 plus 1 over 9 times 2, eventually we'll get to 1 over 1 plus 9m, and then we'll have 1 plus 9 over 9 times m plus 1 forever and ever. Well, when I'm underlining, that's this. But now I'm multiplying by more, and each of these numbers are more than 1. You keep multiplying by more than 1, you get bigger. You multiply by more than 1, you get bigger. That is why this symbol right here is absolutely correct. Okay, let's erase this, and let's talk about what we can do from this. Now, it turns out that this is going to be bigger than 1 over 9 plus 1 over 18, all the way up to 1 over 9m. I want you to think about why that's true. Actually FOIL it out and only keep those and throw everything else away. That's why this is bigger. This only has some of the products over here. But very importantly, all those terms are positive. So what you're throwing away, what you're not including here, are positive things. Well, since you include them over here, this side is going to be larger. But now this right-hand side is, factoring out 1 over 9, is 1 over 9 times 1 plus a half, because 1 over 9 times 1 is 1 over 9. 1 over 9 times the half is 1 over 18. And I didn't mean to close the brackets. All the way up to, oops, put this 3 dots in, all the way up to 1 over m. Well, this does equal 1 over 9, keeping in mind that's 1 over 1. This is the summation. I'm going to write what's in the bracket in sigma notation. Summation of 1 over I as I goes from 1 to m. Okay. Now, I guess at the very, very beginning here, I should have said for all m. Okay, so if I push m, if I let m get bigger and bigger and bigger and bigger, this goes to some number as m goes to infinity. But this is the harmonic series. And everyone knows that the harmonic series diverges to infinity. Times it by 1 over n, it's still infinity. Okay, that is, this here goes to infinity. But this is bigger. This is bigger. Therefore, the product as n goes from 1 to infinity of 1 plus 1 over 9n is infinity. Or I could have said the limit as k goes to infinity up to k. Let me use m. This limit is infinity. But that's what I wanted to show. If this limit was infinity, then this limit was 0. But that's what I wanted to show. Okay, it's a long proof, but it is now proved. No matter what we take balls out, limit 3 is that we rank a ball after we 10 in, every ball will be removed. At the end, whatever that means, at the end, every ball will be in. Okay, I hope this problem. Thank you. Few times clear.